Hello, friend. So today I'm going to be going over problem 1.1 from Griffiths Introduction to Electrodynamics. In this problem, we are asked to use equations 1 and 4 in appropriate diagrams to show that the dot product and cross product are distributive. The first part of this question is asking us to do this when the three vectors are coplanar. I'm going to start with the dot product part of this. So if we take equation 1, which is the vector A dotted with the vector B, we get that it is equal to the magnitude of A times the magnitude of B times cosine theta between the vectors A and B. Let's also define what the distributive property is itself. So the distributive property tells us that A dotted with vectors B plus C is equal to A dotted with B plus A dotted with C. So we're going to be trying to prove this equation here in this video. Let's start with the appropriate diagram. So in the left-hand side of the equation, we have a vector A, and we also have a vector B plus C. Now I'm just writing the little vector notation on top. B plus C, if we remember how to add vectors, I can take a vector B and a vector C, where the second vector goes from the head of the first, and then our addition is from the tail of the first vector to the head of the second vector. I am in this also going to write out some angles. So we'll say that theta 1 is the angle between vectors A and B. If I draw a little line down from the top to make it perpendicular with A, and then another one right here, this angle between what is perpendicular to A, or I should say parallel to A, and between vector C is theta 2. And lastly, the angle between vector A and vector B plus C, we're going to label as theta 3. Apologies, that's a little bit small. So let's start with the right-hand side of this equation. I'm going to take A dotted with B, and now I can write it out based off of our equation or diagram that we wrote here, that this is the magnitude of A times the magnitude of B cosine theta 1. Reminder that theta 1 was our angle between A and B. Then A dotted with vector C, magnitude of A, magnitude of C, cosine of the angle between them, which we labeled as theta 2. If I add these two together to equal that right side, I get that A dotted with B plus A dotted with C is equal to A, B cosine theta 1 plus A, C cosine theta 2. I will just quickly pull A out front and get B cosine theta 1 plus C cosine theta 2. So this is our right-hand side of our equation. Now let's take a look at the left-hand side of our equation. Here we have that vector A dotted with B plus C is equal to magnitude of A, the magnitude of B plus C. So we're going to treat this like it's one vector. You could label this as D if that made it simpler in your mind. And then cosine theta between these two, which we took as theta 3. And what I will note here is that cosine theta 3, if we look at the adjacent component of the little triangle between A and B, we get that this is B cosine theta 1. This tiny segment here is C cosine theta 2. And B cosine theta 1 plus C cosine theta 2 is our adjacent component of the triangle made between A and B plus C. And if I take the cosine, it's the adjacent component divided by the hypotenuse, so the magnitude B plus C. And finally, if I plug this equation back in for cosine theta 3, we'll see that the magnitude B plus C and the original equation cancels with the denominator, and that our left-hand side, so A dot B plus C, is now equal to A B cosine theta 1 plus C cosine theta 2. And if we notice, this equals the right-hand side of our equation. So now we have proved that the left-hand side is equal to the right-hand side, and that the dot product is distributive when the three vectors are coplanar. So this is the first part of this problem. Okay, so now moving on to the second part of this first part of the problem. We are going to repeat the same process, but for the cross product. So the cross product is given to us in equation 4. So we get that A cross B is equal to the magnitude of A times the magnitude of B, sine of the angle between them. And then the cross product gives us a vector back, so we will label this with a unit vector. And then if I'm considering the distributive property now for the cross product, we'll get that A cross B plus C should be equal to A cross B plus A cross C. And that's what we're going to prove now. So if we start once again with the right-hand side of the equation, we get A cross B is equal to the magnitude of A times the magnitude of B, sine of the angle between them. As we stated before, this is theta 1. And then I'll just keep that n hat at the end. A cross C is equal to magnitude of A times the magnitude of C times the sine of the angle between them, which we labeled as theta 2 with the n hat. And if I combine these together, I get that A cross B plus A cross C is equal to A B sine theta 1 n hat plus A C sine theta 2 n hat. And finally, pulling that A out, that A is equal to B, or A times B sine theta 1 plus C sine theta 2. And I'll just leave the n hat out front, or at the end. Then if we take a look at our left-hand side of the equation, we get that A cross B plus C is equal to the magnitude of A times the magnitude of B plus C, sine of the angle between them, labeled here as theta 3, the n hat. And in a similar fashion, if we look at the sine of theta 3, we get that the sine components, if we look first at this smaller triangle between B and A, we get that the sine component is B sine theta 1. Here, this y component, if you want to call this an xy plane, is C sine theta 2. And therefore, the full opposite side of the triangle between A and B plus C is B sine theta 1 plus C sine theta 2 over the hypotenuse, which is the magnitude B plus C. Plugging this in for sine theta 3, the magnitude B plus C here cancels out with the denominator here. And finally, I get, can't see that A cross B plus C is equal to A times B sine theta 1 plus C sine of theta 2 in the n hat direction. And as we see, our left-hand side is equal to our right-hand side, which it should be if we're proving that this distributive property up here is correct. And so we have done that. Now moving on to part B of this problem, we are asked to do the same of showing that the dot product and the cross product are distributive, but now in the general case. So I've gone ahead and rewritten the dot product equation from equation 1 and what distributive means in this case. And one thing we need to start with in the general case is if we consider that a vector A can be written into 3 components for 3-dimensional space. So I'll write this as lowercase a1, a2, a3. You can kind of think of this as like x, y, z. And I can write any of these vectors in the exact same way, broken down into their 3 components. And if we look at the direction of cosines, we can write a1 over magnitude of a2 over magnitude of a3 over magnitude of A. And with this, we are going to then write out the cosine theta. So cosine theta, so this is now between 2 vectors. So let me just write real fast that the vector B is B1, B2, B3. And the direction of cosines tells us that we can write this as B1, B, B2, B, B3, B. And all the direction of cosines is, I guess I haven't explained that, is the cosines of the angles a vector makes with the positive coordinate axes, so x, y, z. And you find them by taking the vector, so these a1, a2, a3, and dividing it by the magnitude, so this total A. Then moving on to finally the cosine theta. So I'll take first the A1 over A times B1 over B plus the second component, so A2 over A, B2 over B plus C or A3 over A, B3 over B. So this is our equation for cosine theta, where theta is between A and B. And then if I plug this kind of back into our dot product equation, I get that the magnitude, or vector A dotted with the vector B, is equal to the magnitude of A times the magnitude of B. Here I'm writing in lowercase. The uppercase would also be fine, but just to keep it consistent with what I've written already. And then times our cosine theta, so A1, B1, plus A2, B2, plus A3, B3. All of these were over the magnitude A times the magnitude B, which will cancel out with that first term. So therefore, the dot product in the general case between any two vectors is A1, B1, plus A2, B2, plus A3, B3. We are going to use this to prove now that this distributive property is true. Let me clear the board and we'll start writing that. So I've gone ahead and rewritten that equation that we just solved. So this is a vector A dotted with a vector B written in the general case. So the individual components of the vectors multiplied by each other and added. So now if we're looking at this distributive property, we already have A dot B. We can also write A dot C simply as A1, C1 plus A2, C2 plus A3, C3. And if I combine these on the right-hand side, so let's just label this, I get that A dot B plus A dot C is equal to A1, B1, plus A2, B2, plus A3, B3, this whole thing plus A1, C1, plus A2, C2, plus A3, C3. I am aware this is a bit redundant, but for completeness, I wanted to write it out. So now for the left-hand side of our equation, we're going to take A dot, let me write out left-hand side, B plus vector C. This is the same thing as the magnitude of A, or I've been writing this in lowercase. Let me write this in lowercase. So the magnitude of A times the magnitude of B plus C times the cosine between these two vectors. And we found here, if I write this out in complete form from before, that this is the same thing in the general form as A1 times B1 plus C1 plus A2 times B2 plus C2 plus A3 times B3 plus C3. Now, if we just distribute this, because these are all scalars at this point, I can write A1, B1 plus A2, B2 plus A3, B3. Now, I haven't ignored these other components, but you'll notice if I write out the rest of them, so A1, C1 plus A2, C2 plus A3, C3. This is now, so this left-hand side that we just solved for is now identical to the right-hand side that we solved for right up here. And we've therefore proved that in the general case, the dot product is distributive. All right, last part. So I've rewritten equation 4 up here, the cross product definition, and what we're going to be trying to prove that the cross product is distributive. I want to note in the general case that we can also write this cross product a little bit differently. So I can write that A cross B is the same thing as the determinant of the matrix if I break down all the elements of A and B. So these are unit vectors I in the direction 1s, 2, and 3, or you could write this as x, y, z. And then in the individual directions, I have the components of the vector A, and finally the components of the vector B. So there I have a 3x3 matrix with the unit vectors components, the vector components of A, and the vector components of B. If I take the determinant of this 3x3 matrix, so let's do that real fast, I get that A2 times B3 minus A3 times B2, A3 times B2 times I1 is my first component of this new vector, because a reminder, a cross product gives us a vector. Then the second part of the determinant, I take the minus sign of A1 B3 minus A3 B1 in the second component. And finally, for the third component, I add A1 B2 minus A2 B1. And so this gives us our three components of our vector that we get crossing A with B. So this is for the general case of just two vectors. But now if we're going to go back up to this distributive case, we have A cross B. I can also rewrite A cross B for A cross C. But what I'm going to do instead of writing everything out and being redundant is if I take my distributive property equation that I have up there, I am only going to work out one of the components of the left-hand side and see if it equals my right-hand side. So I'm going to call this whole term on the left the vector D, and then this first part on the right-hand side, vector E, and the second part, vector F. Now the first component of D, so I'm going to label this D1, is equal to A1 times B3 plus C3. I'm just getting this, this should be A2 times B3 plus C3 minus A3 times B2 plus C2. And so this is just that first component broken down instead of between A and B, now between A and B plus C. And this is all in this first direction, so I don't need to necessarily label it with the I hat. And if I distribute this out, because now these are all scalars, I have A2 B3 minus A3 B2 plus A2 C3 minus A3 C2. And if we notice, if I take E1, So this is just between A and B. We already found that that first part of the first component of E was A2B3 minus A3B2. So right now we can see clearly that this is equal to E1 plus F1 is A2C3 minus A3C2, which is the second component of D1. So this is F1. And so if the individual component of D, so D1, is equal to E1 plus F1, then it's fair to say, and you can work it all out for yourself for each individual component if you would like, that D vector is equal to E vector plus F vector. And that's the same thing as saying in this general case that the distributive property of A cross B plus C is equal to A cross B plus A cross C. And, or I guess you can look at the one down here. And therefore we have proved that the cross product is also distributive in this general case. Thank you so much for listening in on this video. I hope it was helpful for you to see this all worked out. If there's any specific problems you would like me to solve, please let me know in the comments. And if you have any questions, please also write those in the comments, and I will see you again in a future video.